Well, hello there. My name is Ron. Welcome to the Bell Experience. I'm excited to have you here today. And what I've got for you is a technical learning conversation, a technical use of engineering principles that we will take to the next step and do as a deep learning activity when you arrive at the Bell Experience. So let's get started. What happens a lot in engineering is we have tanks filled with some fluid, and then those tanks have to drain. And one of the principles that we use is the principle of the conservation of mass, and then another is the conservation of energy. So in our particular example here, we've got a tank, and the tank has some fluid in it. Let's use water. And we're just going to let the tank empty. And our question is, how long does it take to empty the tank? So maybe we would start our stopwatch up here at the highest height and then call that time equals 0, and then stop it down here just before the water starts trickling out, and we'll call that our final time. And we want to use engineering principles to predict how long it's going to take. The first principle is the energy principle. And the equation for the energy principle is the pressure acting down at point 1, up here, this is point 1, and we'll let this be point 2, plus the height of point 1, plus the velocity of the fluid at point 1. Now those units don't work, so we need to adjust them. We'll divide this by the specific weight of the water, like water is 62.4 pounds per cubic foot, and height is good. We square the velocity and then divide by 2n gravity. And what we end up here with is like, this is potential energy, this is kinetic energy, this is doing work. We have some losses due to friction. We call that head loss. And then at the second point, where we are driving from point 1 towards point 2, we have pressure 2, height 2, velocity 2 squared over 2g. That is the energy principle. You'll often hear it referred to as Bernoulli's equation or Bernoulli's principle. Conservation of mass is also known as continuity principle. And the way we're going to apply the continuity principle is we're going to say that the volume, V with a squiggle is volume, flow rate, the dot is a flow rate, the volume flowing down equals the volume flowing out. The volume flow rate at 1 equals the volume flow rate at 2. I like to say the goes into's equals the goes out of's. Now the equation for volume is, or volume flow rate is area, so we could measure that diameter and get that area, times velocity. How fast is it moving down? And area of the hole times the velocity of the fluid flowing out of the hole. One equation, two equations. What we're going to do now is we're going to manipulate these two equations so eventually we can find out how long it takes. So let's get started. First thing I'm going to do is I'm going to solve this equation right here for velocity 2. So velocity 2 equals area 1 times velocity 1 over area 2. We'll need that later. In step 4, we're going to simplify the energy principle. So I'll write it out here again. And we'll see, are there any things in here that are 0 or that cancel out from one side to the other? We're going to make a simplifying assumption. We're going to assume that the friction is negligible. And when we get to the real world and we're out in the lab measuring this, we'll decide if that was a good assumption or not. This pressure is the atmospheric pressure acting on the surface of the water. And this pressure is the atmospheric pressure acting on the surface of the stream. And those are the same. Atmospheric pressure is the same. So we can actually cancel that out. That's not an assumption. That's a truth. So let me rearrange this here. In fact, I think I'll rearrange it and I'll put the heights together on the right side and the velocities together on the left. what I like to do is go through and look and see what do I know and what don't I know. When we go into the lab, we'll be able to measure how high is the top of the water to the top of the hole. And, you know, it might be 3 feet, it might be 3.5 feet. We'll find out when we get there. So I just used 3 feet here to frame our minds. But we're going to know these things. What we won't know is how fast is the water flowing down and how fast is the water flowing out. So we don't know these two things. And this is one mathematical equation. And that would be a really sad face, because we can't solve one equation for two unknowns. But we've got our second equation over here. And if we substitute, use the method of substitution to put in place of this V2, that area 1, area 2, and V1, what would that look like? Be area 1 V1 over area 2, and we have to square everything. Squared, squared, squared over 2G equals Z2 minus Z1. We could probably take this 2G and move it up over here. And I think we can solve this for V1. In fact, I think I can factor out a V1 squared here. And I get V1 squared times 1 minus A1 squared over A2 squared equals, let's put the 2G in front, 2G times Z2 minus Z1. And I think we can measure all this. We could take our tape measure and measure the diameters to get the areas. We can measure the heights. We know gravity. This velocity is the only thing we don't know. And let's just take one more step here and say, all right, velocity 1 equals 2G times Z2 minus Z1 over the quantity 1 minus A1 squared over A2 squared, and take the square root of that. And I think we're in good shape. I think we've got the ability to solve for the velocity of the water flowing down at that point, knowing all of the physical characteristics of the tank, its heights and its areas and its hole sizes. Awesome. Now, how are we going to use that to get how long it takes to empty the tank? Well, let's go over here to step 5. I believe that velocity is equal to distance over time. I think you probably agree with me. Oh, let's solve that for time. How about then time equals distance over velocity? So if we know the velocity up here, and we know the distance that it's going to travel, we can calculate how long it's going to take. So let's say we did this and we got V1 was 40 feet per second, and we know that our height is 3 feet. We could put in a time, put in a distance of 3 feet, divide by 40 feet per second, and we'd get our time. All right. Oh wait, we have a problem. If we did that and we went out to the lab and measured it, we'd be way off. And here's why. However fast the water is moving at, say, 3 feet, a moment later, there's less potential energy, so it's going to be moving slower. And it will continue to get slower and slower and slower and slower and slower all the way to the end. So this assumption or this approximation wouldn't be very valid. So here's what we're going to do instead. We will do this, and we'll do it when our Z1 is 3 feet. And then maybe we'll break it up into 1-inch increments. And we'll see how long does the water take to fall 1 inch. And we'll calculate that time. And then we'll say, okay, now Z1 isn't 3 feet anymore, it's 2 feet 11 inches. And we calculate a new velocity. Our new distance is 1 inch again. Our velocity we put in, we get a new time. And that's how long it takes to go the 2nd inch. And then we could do it for the 3rd inch. We could add all those together. And then we would have a really good approximation for our time. All right, well, that's what we're going to do when you get here. We wanted you to have a little time to prepare, to think about it, to get your mind wrapped around some physics principles. And we will use those principles, and then we'll go out into the lab and measure. We'll do some hands-on learning. Look forward to seeing you.